DC microgrid innovations. And you can find more information on our website, www.invantage.com, or directly at the volumetric.solar website. So I'm Aleks Milikovic. I'm the founder of Invantage Consulting. I'm a professional electrical engineer, and I'm also a patent inventor. So volumetric solar, revolutionary 3D solar generators. And it's revolutionary because we on planet Earth are constantly spinning, and the sun for us is constantly moving. It moves throughout the day, and it moves seasonally in the sky, north and south. And so that is the reality of how we need to capture solar power in 3 dimensions. There are 2 types of solar power. There are 2D photovoltaics, so the solar power that you're used to with panels. And there's concentrated solar power, which is a form of solar power that uses mirrors and reflection to generate heat. So we need to find a way to combine direct sunlight and reflected sunlight. And that's what volumetric solar will do. So before we can solve these kind of global problems with solar power, we need to understand that 2-dimensional photovoltaics, 2-dimensional solar power, doesn't work well in the winter. In fact, there's huge losses. Not only is the sun lower in the sky, but because of snow and variable weather, there's huge monthly losses. And this analysis by Sandia National Laboratories in the United States found monthly losses as high as 100%. 100% monthly losses isn't going to work. It's not going to work in cold climates like Canada. It's not going to work in most of the Northern Hemisphere. And every second that solar photovoltaic panels are covered with snow or not receiving sunlight, that results in less power over time and less energy. And the way it's solved today with 2D solar is manual snow clearing. So people go out and clean the snow off the panels. But what we're seeing out of Germany and other countries where they're rapidly installing photovoltaics and they have snow is that adding more capacity isn't enough. And if you look at every year here in this chart, there's more and more power in the summer because more panels are installed. But in the winter time, when there's snow in November and December, you're not seeing the gains linearly going up for more installed panels. So something else is happening and resulting in less energy. And these are huge changes in energy between seasons. Why is this happening? The best example, or the simplest example I give people, is that solar power today, 2-dimensional solar power, flat panels are wired just like holiday lights, mini lights. So you can't buy series connected tree lights anymore, mini lights, Christmas tree lights, because they have some certain problems. They're a single point of failure. So if one bulb goes out on your string, you lose the entire string. And that's just the fact that electricity flows and they share the same current. If one bulb goes dim, the entire string goes dim because that one bulb has less current and all the other bulbs suffer from less current. And that's the same with solar panels. That's exactly how solar panels are wired today in series. And so that understanding is critical to how we're going to solve this problem. The amount of current is directly proportional to the amount of sunlight that's received by each panel. So in a string of solar panels, that's why all of the architecture of solar panels today in 2D, those panels have to receive the exact same amount of light. If one panel is tilted away, it makes slightly less current and the whole string suffers. So that's why we have these linear arrays. So the wiring method of solar panels is what dictates the linear architecture of 2D solar arrays. Let's look at parallel wiring. How did we solve this problem for mini lights on a tree? Well, with wiring in parallel, you lose one light, or one light goes dim, the rest of the lights in your circuit continue to operate. This is critical for improving resiliency, and it also has the major important effect of adding all the currents together. So every single light has its current added together in the string. So the output is a combined output. It's automatically added together. Why don't we do this for linear solar panels today because the parallel wiring is not economical over long distances. So the further your distances are, the more parallel splitters and wiring and cable you need. So compared to daisy chaining in series with photovoltaic panels, there's way more cabling costs when you do that linearly over two-dimensional area. So this is key, that the currents are automatically added. So if we want to get more current, and our power is voltage times current, we need to find an architecture, a vertical architecture in 3D to enable this parallel wiring. A couple more benefits of volumetric solar architecture, just to go through it. Instead of just monofacial panels, bifacial panels. So we collect light on both sides, front and back. We've flipped the architecture to vertical PV. You can see different angles here, and this is testing in Edmonton from Nate, and they installed this test array, and the only architecture that fully shed snow automatically was this 90-degree architecture here. So the example on the left here, the panels were cleaned, and the example on the right here, the panels were not cleaned of snow. But you could see at the top, in all cases, in both cases, these vertical sheets are clear. So understanding these improvements, we've switched to parallel wiring. We've gone bifacial panels. We've gone 90-degree vertical. There's a few more improvements. So the parallel wiring now looks like this. Plug and play connectors. Here's a 4-to-1 connector, plug and play MC4s, and one output on either end. The same solar clamps that are used today and the same panels that are used today, we need to be able to incorporate those into a new architecture. So adjustable solar end clamps are exactly what we can use in volumetric solar. Extrusion T-slot channels lets you put clamps on any side and adjust those clamp locations up and down. Freestanding legs, so the ability to add different attachments to the legs and have a freestanding structure, eliminates a lot of the issues about installation area and space. So what does this all look like when it's combined? Here's a volumetric solar 4x1 tower. This is a rendering on the left here, and you can see there's 4 posts and 4 bifacial panels. With these 4 panels, we combine the current from all sides. So instead of having a flat 2D area that's essentially 4 square meters, 2 by 2 meters, we can combine all the different sides together, the outside faces and the inside faces. You're collecting rotational energy on all sides, inside and out, and adding those currents together automatically in parallel. That's the revolutionary part of volumetric solar, is that the parallel wiring enables that. And we're not losing any power. We're adding all the power together. If we wanted to scale this, we could just add another 4x1 tower right next to it. And then we have a choice. We can connect the output of those parallel connections in series or in parallel. So if we do series, the voltage increases. If we do parallel, then the current increases. So we can create very high currents with limited area use, and we can scale that horizontally. But we can also do that same thing vertically. So that same structure, using the same 4 posts, you can scale it up and add more units up. Each one of these panels in this 4x2 can do up to 25 amps individually. Here's an MIT study on cubic structures. They did these comparisons and calculations over seasons on how much more solar energy can be generated in 3D compared to using that 2D flat surface. Here, like in Canada, the ratio, so the amount of energy with a 4-sided cube compared to flat, is 3.4 times over an annual basis. And you can see really in the winter months, the multiplier goes way up the higher in latitude. So I built these 4x1 structures and 4x2 structures, and I can tell you in the winter time, they automatically shed snow. You don't have to manually clear them. They heat up on the inside and outside, and you get more power from the snow reflection. Snow is highly reflective. It is probably the most reflective surface that naturally occurs. So you get power from above and power from below automatically in a rotational way with these structures. So if we're going to decarbonize the grid, transportation, heating, agriculture, and industrial processes, we need to use direct sunlight and reflected sunlight to create DC electricity and then apply it for these applications. And with wiring in parallel, you can do that. But if you wired in series, it's really difficult to collect that reflected light. Using low-cost reflective surfaces, so aluminum, glass, you can increase the power in the summertime when the snow isn't there anymore. How do you use this higher current? The best way to use this is to charge batteries. So you can take DC electricity generated from these structures and create higher currents and directly apply that into a DC battery. And DC batteries can receive 100 amps, 200 amps or more, and can be wired in parallel to accept higher amperages and then move that directly into a chemical battery system. Lithium ion phosphate, lead acid, they all work in the same way. We can also do high current joule heating. So we take that same electricity, and you see this example here on the left. I'm taking solar electricity as DC and putting it through a resistor element. You can do electric hot water, store that heat in water. You can do electric thermal, geothermal, so sand batteries here in this example. You can heat these temperatures up and create containerized thermal storage at very low cost. The other one is green hydrogen production and electrolysis. So electrolysis is taking DC electricity and putting it through an anode and a cathode, and then essentially with water in this case, the water then splits into oxygen and hydrogen. But what you need is high current. So if you applied the high current and you use mirror reflection to increase the current even more, you can do green hydrogen production off grid. And so rather than the idea of extracting hydrogen from fossil fuels and moving it in a pipeline, you can take water anywhere. So that's the engineering and the technology side. And now we move into microgrid architecture. So microgrid architecture is a brand new field that's enabled now, where we can plan and create 3D photovoltaic structures, 3D volumetric solar structures. So these structures can be mounted on the ground, and they can be really simple, low structures, less than a meter in height, or you can make tall towers. And the taller your tower is, the more power it generates and the more energy it collects. So those structures can be on the ground, which is easy, to assemble. They can also be on rooftops. So you can put them on the apex of a rooftop and have the legs on either side. Installing on roofs is way faster now because you only have 4 points of connection. So you can have 4 connection points instead of having to deal with the entire roof condition. You have to take an old roof here, like this example, and essentially figure out when it's going to be replaced and when you're going to lay all your flat panels and put all your struts across. You don't need to do that anymore with volumetric solar and a 4-post design. You can essentially spread that structural weight evenly across the 4 posts. And so putting this right above chimneys, next to chimneys, you can drop that DC electricity down, and we can get into those joule heating applications where you're providing DC electric heating from the top down. You can put it next to heat pumps. You can put it next to HVAC equipment. You can put it next to a UPS and plug and take that DC power, turn it into AC, and feed your UPS. Let's cut to the business case. So with volumetric solar, you're reusing all the same solar components you already have. You're reusing the bifacial panels. You're reusing the adjustable end clamps. And you can also use aluminum extrusions, which are commonly used as the racking system on flat roofs. Instead of doing those horizontally on the roof, you would flip those vertically into these 4-post structures. So your material costs are the same. In fact, they're less because you don't have as much space requirements. And then so the licensing model on my side as the inventor is super simple. 4x1 is a $200 lifetime license, a 4x2 is a $400 lifetime license, and a 4x3 is a $600 lifetime license. So that's the IP. You can buy it from the volumetric store. You can start assembling these towers anytime. Again, connect those panels in parallel, and you're automatically adding all of the currents together. And then from there, adding reflection when it makes sense to do so, and saving space as well. So these revolutionary 3D solar generators are available today.